Okay. Right. The center of gravity. We have heard of this before? Yeah? So did you all get the title? Moments and center of gravity. Yep. Right. Who knows center of gravity? Who's heard that before? You've probably heard it before?
Yeah.
What would you say it is?
It is
Yeah?
the point in an object or
Yeah.
mass
Yeah? Yeah?
which
Yeah? So far so good.
Where forces are applied.
What type of forces? Do we know this? Yeah? Nearly? Not quite. The centre of gravity of an object is the single point through which the full weight of a body appears to act. So, in other words, if you have some mass, it's the point where the weight seems to be pulling it from. Okay, you'll need that. So basically it's where the weight vector acts. You got that? Yeah, you got that? Yeah, continue. Another way to think of centre of gravity is it's like the average point. Okay, so we want to answer the question, describe a simple experiment to calculate the centre of gravity. I don't know if you've seen this experiment before. How can I find this point? Does anybody know the experiment? You think you might know it, Regina? You're not sure? So what you do, you think you know it, Harry?
You need 2 lines.
Yeah, you need 2 lines. So what you do to get the first line, you have what's called a retort stand, and then what you do is you hang your mass, and then you have a string that hangs down as well with it, and on the string is a little bit of a weight. I think you call this a bob string or a bob or something. And then you just take a pencil and you mark in this line. Okay. Then what you do, you just hang it from I don't know. You just hang it from a different point then. So you still have the first line on it. Oh, it's not great. And then there it is again. And then you draw your, then you draw your new line. And where these two meet, that's the center of gravity. Okay. So,
be a 3-dimensional object.
oh yeah, sorry, in my example it's a flat object, just to make it easier. Oh yeah, I don't know what you'd do as three-dimensional. That'd be a lot harder, wouldn't it? I think the experiment is always with a two-dimensional object, like something like this. So you just hang it from one corner, and you have a line straight down, and then you hang it from another corner, and you have a line straight down, and then where they meet, the center of gravity. So sometimes in the exam, like for 3 or 4 marks, they might say, describe an experiment to measure the centre of gravity. So we need to put some little English here, but we don't like English. I know we don't. So what's the simplest, shortest way we could describe this experiment? Oh, and it's always good. It's always good to draw the pictures too in the exam. No, wait. We need to think of the English here. What could we say? We could say something like, hang the mass. No, I'll write it down, don't worry. We're just talking out loud. Hang the mass from 2 different points on a retard stand and using a bob. Oh, the sentence is getting so long now.
Or start from one point and then the next step is
Just repeat. Repeat step 1. Done. Yeah, okay. Yeah, we could do it as points perhaps, might be easiest, huh? So you could say, hang mass on retort stand. Something like that. Keep it as simple as possible. And then mark vertical, vertical line using a bob. I think it's called a bob. I think it has some other name. Yeah, no, there's a special name for it. I can't think of what it is. Repeat at different point or hanging point. And then lastly, center of gravity is at the intersection. I think that's the absolute minimum I could write to describe this experiment, right? I don't think there's any words I can delete. Hang mass on retort stand. Mark vertical line using... Mark vertical line... I'm not using, that's the wrong verb here. Yeah, that's better, I like that. Along bob line. Yeah. Yeah. If you gave me that with the picture, that would be full marks.
So I need to ask, who marks the final papers?
It's 2 people, so I mark it first, and then it gets marked in Manchester. Okay. We got that? Nope. How are we doing? We have that? For me, the secret is, if you remember the picture, you can think of what sentence to write in the exam. likely to fall? So ABC, what do you think? A, because
Is the highest center.
yeah, the center of gravity is the highest. So when the center of gravity is high, it makes falling more likely. So a little bit of vocabulary now. Does anyone know the word fulcrum?
Fulcrum and leva.
Yeah, yeah. What's fulcrum is another word for what?
The point at which.
Yeah, Yeah. yeah. Go on, you have the.
Fulcrum is.
Yeah. That's another name for it. The point. Oh, come on, you nearly have it. The fulcrum is another word for a turning point or a pivot.
Pivot, yeah.
It's the point at which the object turns. So, I'll show you some examples. Here is a fulcrum right here. Look, I even have the arrow from last year where I drew up the door. This is the fulcrum here, also called the turning point or the pivot, because it's where the door turns at this point. Yeah, that's one example. Another example: the hinge on a door, the center of a seesaw. So you know a seesaw the kids are on goes up, down, okay? Another one, the wheels on a car. And the last one, your foot on the ground. So when you think about it, as you walk, can you look? When you put your foot down, that point is like the hinge on the door. It's a turning point because your foot is turning. Because it's like you're going like this, you know, as you're walking. Okay. So these are all fulcrums or turning points or pivots, you can call them. Okay, so you need that definition, that vocabulary. Yeah?
Is door hinge one with.
I don't think so. Oh, well, maybe you could put a hyphen. Because you see, door hinge, the door is a, well, no, I guess it's not redundant. I think I would put a hyphen there.
Nice, yeah, space. Just
Yeah.
separate.
I say I don't think it's one word.
Yeah, it's two words.
Yeah. Okay, you got the definition? You don't need to write the examples. You can think of your own examples. Any other examples you could think of?
Claw over
Yeah.
there. The poles.
Yeah, they're turning. Yeah. Anything else? So let's see. You know, like the clock, the turning. Where's the fulcrum for the clock?
In the middle.
In the middle. Yeah. What other examples could we have? I suppose if you think about like a sport, something like baseball, you know, when your arm is turning, where's the turning point? Yeah, the shoulder. Yeah. Or, well, you see, it depends what you're doing. Yeah. You could also, you know, if you're, what's it called? I don't know, but you have this move in baseball where you just gently tap it, isn't it? A putt, is it? Who watches baseball? Anyone watches baseball? No? Okay, anyways. But if you're going for a full swing, a lot of turning is happening. Well, your whole body, really, isn't
I
it?
think it starts with driving in both.
It starts with the foot too, doesn't it?
Foot,
Yeah.
while you're spinning.
So many turning points, really, isn't there?
And in skiing, when you are doing a full turn, would be the skis or a point somewhere like really far.
Yeah, it's it'd be far away from the skis. Because it's like
Yes,
it's like you're
like
turning
a
around a
hammer,
point. Yeah.
So,
So-
you're here but you're spinning, so it would be somewhere.
Yeah, exactly. Yeah. So the turning point, you don't need to consider it actually in the object. It could be away from the object, like in the skiing example. Okay, so notice how the ballerina, her center of gravity is above the turning point, and also here is quite small. So she could easily fall. This situation is very unstable. A little push, if I was to push her off, she would fall. Now I wouldn't do that, but if I was, I think it'd be quite easier to knock her down, right? So this is very unstable. This situation here is just unstable. Again, the center of gravity is high up, isn't it? But the base is kind of big. So, yeah, I could knock it over, but it's not very easy, right? But it's still unstable. Notice how the center of gravity is above the turning point. So it's like here, turns here. And the base is kind of big. So it could fall. Now, have you ever seen these toys before? I used to have one as a kid. You've seen it, yeah. The bird balances perfectly on your finger. You know this toy? You know? Didn't have this one as a kid? No. This is something cheap you pick up from the Euro shop for like €2, or at the time £1. So it balances perfectly on your finger. The center of gravity of the bird is exactly on its beak. So it balances perfectly on your finger. Beak is there. So it doesn't really fall, because if you hit it, it just kind of moves a little bit, yeah. So the center of gravity is at the turning point. So a little force could make it wiggle, but it wouldn't really fall. Okay, this is actually stable, as long as he's still holding on. Because if you push him, he doesn't fall. All that happens if you push is it just kind of wiggles back and forth. You know, it doesn't fall. It's not like this. You know, this is very unstable. If I push it down, it goes. But if I hit this, it just goes back to the center. It doesn't fall down, you know. So this is actually stable. Yeah. And the last one here is very stable. The base is very big, isn't it? Center of gravity is here. Turning point is here. You push that in, and very quickly and easily it just goes back to how it was beforehand. So just to really summarize the key ideas here, my physics teacher used to draw it like this at the circus. So if the person is standing on the rope, you know this one, the center of gravity is above the turning point, so we say this one is unstable. This one here, the center of gravity is here, so we say this one is neutral. So, I mean, you could turn a little bit, right?
Yeah.
A little bit, yeah. Could even maybe do a trick and swing around the rope, okay? Here, if he goes a little bit to the left or a little bit to the right, that's a bit bad. Down he goes. And lastly, this, oh no, the head is usually above the arms. This one here is actually stable. The center of gravity is below the turning point, so you could get a swing going. Okay, I think it'd be great if you could draw this picture in as the three situations. 47, you say, huh?
7.
47, 7 is fine.
Oh, so the difference is still 40, though. Okie dokie, we got that?
the stable one is the same as what happens when they are walking with that long thing.
Yeah,
Because the gravity.
pulls it down
Yeah.
if the weights are heavy enough. I think they just.
It's also because the
It bends.
weights are it
Yeah.
bends and it's behind.
I think they probably use that for training, is it?
Oh, they also do it for like long rows.
Oh,
depends on,
yeah. Yeah. There was the fella recently, they had some tightrope walking in Russia recently. I don't know, I saw that on the news, like between two buildings.
Really?
They had some like competition or something that a few people walking across.
Well, nowadays you are attached, so it's alright.
No, not attached. No, free.
Free.
Yes. Not good to watch. Alright, you got that? So okay, now I've already done that. Describe a simple experiment to determine the centre of gravity. I don't know why that's there again. We did that earlier, so. Right. The moment of a force. Does anyone know this? The moment of a force. No? Moments? No? No? Nobody? Is the force times the perpendicular distance of the fulcrum. Basically, it's a turning force. Another word is moment or torque. Now, before you write this down, I just want to explain. Before you write it down, let me just explain. So, let's say here is your turning point. And here is your lever. Okay? And then what you have here is, this is distance D. And then you push down with a force F. Yes? You say you turn, you have a moment equal to F multiplied by D. Also called torque, also called turning force. There's many names for it. It's the force times the perpendicular distance. Now that's fine, right? Force times distance. What happens if the distance is bigger? You get more of a turn. Or if the force is bigger, you get more. Fair enough? There's a little complication if it's at an angle. I want to draw you the two pictures. So you could have a situation like this where the force is being pushed at an angle. There's two ways to calculate it in this situation. What you could do is resolve it this way and this way. And which do you use, do you think, fx or fy? Fy, good. So you could say that you have d multiplied by fy here. Okay? But another way to calculate it is as follows. If the force is at an angle, what you could do is draw this here. This is called the line of action. And instead you could use this distance. I'll just call this perpendicular distance, d with a little perpendicular. So in this picture you could use perpendicular distance times the full force. So you have two ways to calculate it. Now for us, 99% of the time, it's just easy to resolve and use the Fy. Why don't we use the Fx? Well, if I want to turn this door, I could have the force perpendicular. I could have the force at an angle. Okay, but I cannot have the force going through the turning point. If my force is going through the turning point, I can't turn the door. So you can see in the picture, the Fx is going horizontally through the turning point. It's not going to turn it. But the Fy, which is this way, will turn it. So you only care about the Fy part. The Fx doesn't cause the turn. Yeah? Is that okay? So I think this picture with the definition will be good in your notes. So I'll let you draw this first and then we'll go back to the definition. got the picture? Yes? Yeah?
No,
Yeah.
just made a mistake.
Well, can we go to the definition then?
Yeah.
The unit, of course, is Newton meters. Okay, so if you can write that definition down. Okay, you got that? Yeah. We got that? Yeah. Yeah, okay. Okay. A very particular turning force problem is what's called a couple. This is quite a common turning problem. You can see it when you cycle, because you have actually two forces, and you can see it when you're driving your car, again with two forces. This is a special type of system. The two forces are equal and opposite, but they both work together to make a turn. Now we'll get to the definition. I just want to draw the picture here. So let's take the example with the wheel. Diego, where's the turning point here for the steering wheel?
In the middle.
In the middle. So this is the turning point, the fulcrum, okay? And then you have one hand pushing up here with F, and then one hand pushing down here with F. This makes it turn, right? And this makes it turn. They work together. The total torque will be this one, which will be Fr, plus, because they work together, another Fr, which equals F2R. What's 2R? What is it? Yeah, D, isn't it? Called diameter, FD. Yeah? So, a couple is two equal but opposite forces working together a distance. Oh, I used small d. I should have used a capital D. Sorry. Make that one a capital D, okay? Apart and cause an object to rotate. The total turning force is F. Sorry, write it like this, please. Because I wanted the capital D. Oh, Stephen. I should remember to change that. Okay. Capital D, please. Whoops. Oh no, you're going to see my code. Let's see. Where the heck's it gone? Here we go. Well, I'll have to save it later, but anyways, there you go. You can draw one of the pictures if you think it'll help you.
what if the first two verses are not opposite?
Then it doesn't turn. Then what you've just done is you've broken the steering wheel and lifted it off the car dashboard. So they need to be opposite for it to turn. You got that? Yes? Yes?
Can you put the image of the...
Mine? My beautiful picture? This? Really? Okay. Right. What are you drawing?
So what if like the right force is on the top of the wheel and go that direction?
Oh, okay. What if it's like up here?
Yeah.
And which direction?
Horizontal.
Okay. And the other force? Still the same?
Yeah.
Here and down?
Yeah, no, the top one is go left.
Top one goes left?
Yeah,
And this one?
go down.
The same?
We're still doing it.
Yep. Yes, the turning force is still going to be F4 from here, and this one is also F4. Yeah, the same. Yeah. Well, so I suppose for the steering wheel, they don't have to be opposite in a circle. Okay. Here's a very simple one. No, that's stupid. Stupid. They're all stupid little examples. We'll just do one. We'll just do one stupid little example. I don't know why I have three of them. Okay, I'll give you two examples and then we'll finish. So, the first one is we have a wrench. It's a wrench. Yeah, isn't it great? And let's say that's a distance of 30 centimeters. Pretty hot one. And then you have a force here. Let's make this more interesting. Let's say we pull a little bit of an angle. It's not perfectly perpendicular. Let's say it's 100 newtons. And let's say this angle here is 80 degrees. So it's going to turn this way, isn't it? And I want to know what's the torque. So I'll use force times distance. But do I use the 100? No. What do I need to use? Which one? No, 100 sine. Yeah, because you're using this one. And the distance?
0.03.
Yeah. So that would be 30 sine 80, which is...
29.
What is it?
29.54.
Okay, like that. Yeah? And then the last example we'll do, we'll say, here's a steering wheel, and there's the person putting the force up and down. I don't know, let's say 10 newtons and 10 newtons, and let's say that this distance here, how big is the steering wheel? 40 centimeters? Something like this. So in this example, what is the total turning force? Torque?
Shouldn't it be Newton meters?
Oh, thank you, sorry. And here, what would be the answer?
50, 10 times 40, it's 400.
Oh, you made a mistake. What mistake did he make? 40 centimeters.
Oh,
0.4 times 10. 0.4 times 10. 4.
Newton meters.
Yeah. Remember, the formula is FD. It's one of the forces multiplied by the diameter in a couple. It's 4 Newton meters. Yeah? So who's doing more turning? The first or the second?
Same.
No, the first.
Oh,
It's much more.
Oh, you mean on the
Oh, sorry, yeah. In the two examples, the first one's much more, isn't it? Yeah? Turning force is kind of like a vector. It has a direction. So in this situation, you would actually say, if you wanted to, it's 29.5 Newton meters anti-clockwise. You know this word? And this one here, is it clockwise or anti-clockwise? It's again anti-clockwise. So some people maybe want to write in a minus, but they don't care in the exam. If you really want, you can just write anti-clockwise. All right, as soon as you write those two examples down, then you can go. That nicely finishes us up then. You got both drawn?
I would read most of the videos.
Oh, okay. Make sure you do, okay? Do we have class tomorrow?
Yeah.
Morning?
Afternoon. Well, it's in between lunch.
Oh, okay.
And we have
It's not 9 o'clock.
Yeah, and lunch.
Yeah, you can go once you have it, yeah. I don't think there are many questions on this.
Just a quick question. When they say the torque of a car,
Yeah. That's, I think, the wheel. Because the wheel, the engine,
From the engine.
yeah, it's the engine is given a torque to the wheel
okay,
Spinning
to make it
force of
spin.
the
Yeah.
engine.
Yes, yeah. For some reason, I'm not sure why, but electric cars have more torque. I don't know what it is about electric cars, but they have more torque.
So they are actually better for like off-road.
But the electric cars have to be made to be aerodynamic.
Well, they have instant.
So you couldn't, they're not like big 4x4s, you know? So,
Have instant torque because the electric motor can output its power immediately. There's no revs that have to go.
oh, is that what it is? So
That's why the torque curves are flat.
the electric cars can increase the torque faster, is it?
Yeah, well, it doesn't have to rev up to generate power, and as the car revs higher, the power and the torque increase.
Oh.
Electric motors can output their full maximum power
Instantly.
instantly.
I see. So it's not necessarily that they have more torque.
Yeah, it's just
It's
that
just
the
that they
torque
can.
is flat.
It's a constant torque. So for a mechanical car,
It would go
the
like
torque
that.
fluctuates. Oh, so maybe it's the average torque is
Yeah.
higher for an
Yeah,
electric
yeah,
car
might
because
be, yeah.
it's not wasting
Especially
it.
when you
Yeah, okay.
accelerating from rest.
Yes, I believe that. That makes sense to me. Nice. Okay, I'll see you tomorrow.
Bye bye. See you.